to my YouTube channel. In this video I am going to explain you about Miller indices, one of the topic from condensed matter physics or solid state physics. So before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. So let us start. So today's topic is Miller indices. So this is very important topic as per the competitive exams like ACET or NET. So already I have explained about the crystals and 7 systems of crystals. So please go to that video, and especially this topic is related to uh, the crystalline materials or the solid state physics. So crystals, as we know, the arrangement of atoms which are in regular mode. So if we understand the structure of crystals, then we can clearly understand this topic, Miller indices. So Miller indices are a symbolic vector representation for the orientation of an atomic plane. So especially Miller indices are related to the atomic plane in a crystal lattice. So how we can define here? It is defined as the reciprocal of the fractional intercepts which the plane makes with the crystallographic axis. So Miller indices are, we can say that they are related to the atomic plane in the crystal lattice, and we can define them as the reciprocal of the fractional intercepts which the plane makes with the crystallographic axis. Okay, this is all about the definition of the Miller indices. How we can find the Miller indices? There is a procedure to find Miller indices. First step is to find the intercepts of the plane along the coordinate axis x, y, z. So the second step is take the reciprocal of the intercepts. And the third step, reduce the reciprocals into whole numbers using LCM. That is least common multipliers. Write the integers with the parenthesis, means inside the bracket you can write on the integers to get the Miller indices. So usually Miller indices are denoted by HKL in the parenthesis. So bracket denotes the plane. If we take square bracket, that denotes the direction of the plane. So let us consider here one example. So here the crystal plane is shown in this figure. These are the three coordinates x, y, z. Here the intercepts you can see, as we know, find the intercept of the plane along the coordinate axis. First step is to find the intercept. So here we have joined the lines over all the three coordinates. So these are nothing but what? Intercepts of the coordinate axis. So here we have denoted with A, B and C. So from origin the first distance is what? A for the x axis, y axis B and C. So each time it is increased by one value, like A 2A 3B, B 2B 3B and C 2B 2C 3C. So here we have just drawn the lines. Those represents the intercepts along the coordinate axis. That means here intercepts are what? So here for the x-axis from the origin it is joined. You can see to the A unit. So 1 we can take, and here along y-axis it has been connected to 3B, and along z-axis it is connected to 2C. So if we join all these are what? Intercepts along the coordinate axis. So here 1, 3, 2 we can write. 1, 3 and 2. So reciprocal of these intercepts 1 divided by 1, 1 divided by 3, 1 divided by 2. LCM if we take 1, 3 and 2, that is LCM is 6. So here we can just multiply numerator with 6, then we are going to have the Miller indices. 6 by 1 6, 6 by 3 2, 6 by 2 3. So what is the Miller indices of the plane here? 6 2 3. Okay, like this if you follow these steps you can find out the Miller indices. So what are the features of these Miller indices? First one is the plane passing through the origin has non-zero intercepts. So if the plane is passing through the origin, then it has the intercept that are going to be non-zero. All equally spaced parallel planes have same Miller indices. If the planes are parallel, that means they are going to have the same Miller indices. Miller indices do not define a particular plane, but define set of parallel planes. And if the plane is parallel to any one of the coordinate axes, then its intercepts will be at infinite. Okay, so this point you should remember. If the plane is parallel to any one of the coordinate axes, let us say x, y or z, then its intercepts will be at infinite. Therefore, the Miller indices of that particular axis is 0. Then if a plane cuts the axis on the negative side, then the corresponding Miller indices will be negative. Okay, so if we can also have the negative Miller indices once the plane cuts the negative axis. So here some of the common planes you can see how we can write the Miller indices for the given plane. So here in this first figure we can have the Miller indices, that is 0 0 1. Why? Because this plane is parallel to x-axis and y-axis, that's why 0 0, and it is perpendicular to z-axis, that's why 0 0 1. So like that in the second figure, so this plane is parallel to z and y-axis, that's why it is 1 0 0 plane. So like that you can write for the third figure, that is 0 1 0. So just you should follow these features. So as we know here, the fourth one, if the plane is parallel to any one of the coordinate axis, then its intercepts will be at infinite. Okay, so that's why we can write like this. So reciprocal of the intercept and LCM if we take, we can just write the plane. So here in this case, the plane or the Miller indices are given by 1 0 1. So we can see here this is the plane along the diagonal of the unit cell. So here also it is given by 1 1 0 plane. So 0 1 1. So in this case you can see here we are having this triangle. So this is going to be, it is covering all the coordinate axis, that's why it is having 1 1 plane. So here also it is 1 1 plane, and in this case also. So these, like this you can just draw the plane, or for that plane you can write the Miller indices. So planes are indicated by the Miller indices inside the parenthesis. Then interplanar spacing is also very important to discuss here because it is given in terms of Miller indices. So how we can define here, the distance between any two successive planes is called the interplanar spacing. If we take two planes, then there is a distance between them, that distance is called interplanar spacing. So just let us take this cube. So if we take the planes, here we can see here the just we have taken this part of the plane, then OA, OB, OC, if we take, these are the intercepts from the origin for the plane. So 1 divided by H, 1 divided by K, and 1 divided by L. HKL are nothing but Miller indices. So if we multiply with the lattice constant, so A is what, the lattice constant, that is for all the unit cell. So it is for a crystal, if you take, the distance between each atom is denoted by the lattice constant A. Then we can write here A divided by H for OA, OB, OC, A divided by K, and A divided by L. So here, as I said, the length of the lattice is given by A. If we consider here the triangle ABC, so here let D1 and D2 be the distance between the origin and the first plane ABC and the second plane A prime B prime. Then let D be the distance between the two planes A, B, C, and A prime, B prime, C prime. If the plane, as we said, AB makes the intercept with the coordinate, ABC makes the intercept with the coordinates OA, OB, OC. So these are denoted in terms of Miller indices and lattice constant. So from figure, there is an angle made by all these intercepts OA, OB, and OC, alpha, beta, gamma. So we can use this cos alpha. So that is what base by hypotenuse. So ON, that is here is the N. So ON by OA, if we take, OA is what here, A by H. So ON by OA, ON is what, that is D, interplanar spacing, D between two planes, D by A divided by H, that is DH by A. So like that, cos beta, cos gamma, if we take the angle made by OB and OC from the origin, then we can have dk by A, dl by A. According to law of conservation of energy, if we add all these angles, square of them is going to be equal to 1. Then angles are given by in terms of D, interplanar spacing. Just substitute the values here. So we will get here the equation D square by A square inside the bracket square of the Miller indices, sum of them is equal to 1. So finally we can write the interplanar spacing D is equal to A divided by root of H square K square plus L square. So this above equation is the expression for interplanar spacing. So like this you can just solve any problems related to interplanar spacing and Miller indices. So first you should understand the concept clearly. I hope this is helpful for you. If it is helpful, please like, share.